Good afternoon, guys. How are y'all doing? Good afternoon, everyone. How are you doing? I've been playing with video settings today, trying to try yet one more thing to see if I can keep my screen from freezing halfway through class. We're trying something new. I'm going to share it. When I share my document camera, I'm going to share it as a camera instead of an application and see if that will help at all. Okay, so I think that you can all hear now, right? I've got my volume on as well as my camera. Great. Okay. So I am working my way through grading. I keep thinking that, you know, we're third weekend. Everything is going to get simpler and I'm going to catch up with everything, and I'm not quite caught up yet. But I did get your survey projects graded today. I have very high hopes for the other assignment that you've already submitted to get it done tomorrow. And I don't think you have another written assignment until the book review. Is that correct? Has anybody had it gone in and looked at that? Okay, great. Like I said, I was in the grade book and looking at your stuff, so I was trying to make sure that we were all caught up and I didn't need to send out any more reminders. So count that as your book review reminder. Make sure that you have looked through that rubric, that you have ordered your book, hopefully received it and started reading it by now, so that you're going to not have to rush at the end for that book review. Today we're going over 11.2. We're going to talk about complex experiments, about organized lists and tree diagrams. Mostly that stuff is pretty easy. It's pretty familiar to everyone. Probability tree diagrams are not as familiar, though. You can see the graphic on the screen, and remember you can zoom in on that on your own screen so that you can read a little better. But from the graphic that you see on the screen, it is clear that we are doing a two-stage experiment. We're going to take two balls out of the jar. One really important thing here, without replacement. And the question is, what is the probability of getting two balls of the same color? Now, we're not going to answer the question right now, but I just want to draw your attention to how this tree diagram is structured with the fractions on each branch to show the probability of that happening. Now, when we look at the first stage of the experiment, that represents the first ball being drawn out of the jar. Why is this branch with red have a fraction of 2/9?
Because out of 9 balls, there are only 2 red.
Perfect. Out of 9 balls, there are only 2 red. So I noticed that for my first draw, for the first ball I draw out, I've got fractions all over 9. But when I do the second draw, my denominator has changed. And now all my denominators are 8. Why? I have 9 balls in the jar. Why did I change the way I represented the probabilities? Ah, Saida, yes, we took out 1. That's that keyword without replacement over here, key phrase, without replacement. That matters. If it was with replacement, then for the second draw, we would still have 9 in the jar. But because it was without replacement, we took 1 out and we kept it out. We didn't put it back in, and that changed things. So you'll notice that when we work our way down that red branch, now suddenly, instead of 2 out of 9, we only have 1 out of 8 because the ball that we drew was a red one. The denominator changed and the numerator changed for red, but it didn't change for green or blue because we still have 3 green and 4 blue if the first draw was a red. When I look at the green branch from the first draw, I can see that I no longer have 3 green. Now I just have 2, and it's out of a total of 8 in the jar. Another thing that I notice, is that, well, let me just ask you a question. Are we reducing fractions here? Are all of these in lowest terms? No, Shanique, you're right. They're not in lowest terms. 2/8 would reduce to 1/4. 3/9 would reduce to 1/3. But it is important that you take note of that they did not reduce here. We aren't done with this. This is the probability tree, but we have created it to use. And if you reduce all those fractions that are a part of the tree to lowest terms, you have just created more work for yourself, because you're going to end up needing common denominators. Shanique, correct. Do not reduce until you get to that final probability. So like I said, we're not going to go ahead and answer this question right now, but the question is, what's the probability of getting 2 balls of the same color? I would find all of those probabilities from the tree diagram and gather that together and then reduce my final answer. So this is an example of, like with our card experiments that we did, it ends up being more work for us if we try to reduce in the middle. We just wait and reduce till the end. And that's kind of counterintuitive to the way we are used to doing math. A lot of the time we reduce as soon as we can. Okay, let me go ahead and switch gears and hopefully switch cameras. We're going to see if this works for me today. Oh dear, so so my life just got interesting. So here's what, let me see what happens. I'm going to share this, and it's probably, no, it flipped. Okay, in my preview it was backwards, but it's not backwards in real life, and that's what matters. So there we go, perfect. Now my hope is that the way I'm sharing this today is going to allow me to not have my screen freeze in the middle of class. This was the last page of the activity that we ended class with on Tuesday. We're going to finish this up. So I apologize. We got started on the 11-2 stuff with probability tree diagrams, and now we are switching gears back to empirical probability. Now, what type of probability is empirical? What is another term that we can use for empirical probability? Experimental. Both of those start with E, so it's easy to tie them together. And remember that empirical and experimental probability are the same thing. That means that instead of tying ourselves to the sample space, we are looking at the number of times the experiment was performed or the number of trials. Now, what I asked you guys to do, we're talking about the same 2 Vegas games, Super 7 and 11 Heaven. So Ima is going to Vegas and she wants to know which game to play. Does she want to try to roll a sum of 11? Does she want to try to roll a sum of 7? And when we worked the theoretical probability with this, I don't have that in front of me, but when we worked the theoretical probability, we found that it was easier to get a sum of 7 theoretically because there's more combinations that give us 7. 11 was going to have to be rolling a 5 and a 6. That's the only way that we were going to get it to add to 11. Does this hold true for an experiment? Well, let's see. Now, I asked you to go ahead and do the 20 trials. And I did my 20 trials, and you see I kept track, rolling my red and green die of what the red die read, what the green die read, and then I found my sums. Hopefully you are all here. We're going to try to do some class data with this. So I do need you to have these 20 sums. If you have already done your 20 rolls, go ahead and fill out your count and proportion rows over here. For example, how many times did you roll a 2? How many times did you roll a sum of 3? How many times did you roll a sum of 4? And so your numbers are not going to be the same as mine. Our proportion, each of us is going to have a proportion, that number out of 20. So our denominator is going to be the same, but our numerators are going to be different. For example, I did not roll a sum of 2. So my proportion is 0 out of 20, or just 0. You may have rolled several 2s. I have no idea. So you are looking at your list of sums and doing the count. Yours are not going to match mine. I rolled some really big numbers. And then make sure that all of your counts add up to 20 total rolls so that you know you've got your count correct. I want you guys to let me know, give me a thumbs up or a done in the chat when you have gotten to this point where you have your count and your proportion. We're going to take a couple of minutes unless everyone is already there, and then we'll move on. Great. Got a couple people done, some people still working. Good job, good job. Be sure and double check, make sure your counts add to 20 so that you know you didn't miss one. I missed a 5 and had to go back and put it in. If you have your count and your proportion, go ahead and answer questions 1 and 2. Faith is done, so we've got 1, 2, 3, 4 of us done. We're still waiting on a couple more. I'll give you just another couple of minutes. I went ahead and turned my proportion into decimals just to make that comparison. Sometimes it's easier for us to look at a decimal than it is a fraction with a denominator we're not comfortable with. All right, I think we've got a couple more people who are still working. We're going to need to go ahead and move on just so that we have plenty of time to work with our probability tree diagrams. So I got that Ima should play that 11 heaven game because when I did my 20 rolls, I had more sums of 11 than I did sums of 7. Did anyone else get a similar outcome to me where you had more sums of 11 than you did of 7? Saida didn't. Saida, how many 7s did you have and how many 11s did you have?
So I have 4 7s and I have 0 11s.
Oh, wow. Okay, so yeah, very definitely, as far as you're concerned, your outcomes, she needs to play Super 7.
Yep.
Somebody else speak up and tell me what your outcomes is.
I had 2 7s and 1 11.
Oh, so still need to do 7s, but you didn't have very many outcomes either way.
Yep.
One more person. Somebody else speak up and tell me what you got.
I had 1 7 and 1 11. So.
Oh, so it's just a toss-up as far as you're concerned.
Yeah, she wouldn't do very good.
Yeah. So just so you know, if I'm going to go blow some money, I just assume have dinner and a movie out of it. But I get it that gambling is a draw. So chance, right? It depends on how many times you perform the experiment. It sounds like I was the only one who had more 11s. Let's gather some class data on the number of 7s that were rolled and the number of 11s that were rolled. So here's what I want you guys to do. I set this up for the whole thing. We're not going to do the whole thing. We're just going to focus on 7s and 11s. I need to know, just for 7s right now, I would need to know how many 7s everyone rolled. So type that into the chat, the number of sums of 7 that you had when you did your 20. Okay, so we've got 6 outcomes there. 1, 2, 3, 4, 5, 6. And I rolled as well, and I had a total of 3 7s. So if we add up our class data, that's 3, 4, 5, 6, 7, 11, 15, 17 is what I'm coming up with. A total of 17 7s. And that was 1, 2, 3, 4, 5, 6 of you plus me. So that's 7 people. And if we each did 20 rolls, that's going to be 140 rolls. So we had 17 sums of 7 out of a total of 140 rolls. Everybody with me? What about 11s? So we've got 0, 1, 1. I need one more outcome, I think. There we go, Judy. Okay, so Saida, you were the first one to type in. I had 4 11s, so we're going to add in my 4 plus Saida's 0, and then that's 4 and 1 is 5, 6, 7, 8, 9, 10. I get a total of 10 11s in the class data out of 140 rows. So if we look at our class proportion, we have 17 rows that had a sum of 7 out of 140 rows. We had 10 that were a sum of 11. Turn those into decimals for me. Give me 2 decimal places. How are you going to turn those into decimals for me? Saida, all right, that 17 divided by 140 is going to be 0.12 if I round it to 2 decimal places. What about 10 divided by 140? 0.07, we're going to round it to 2 decimal places. So if I look at either the fraction or the decimal form of my class results, I very much want to tell her to play Super 7. Because we almost got almost twice as many outcomes as 7s as we did 11s. Did not match my data. I didn't do it wrong though. It's just that with empirical probability, it's based on your particular experiment. The more data you have, the closer you get to what we expect as an outcome. If you look at, I don't have the theoretical page in front of me. That's okay. Any questions about this activity? The difference between empirical or theoretical, something we did with class data. Any questions about this before we move on to today's topic? Okay. I'm going to assume everybody's good. Let's set that aside. And you need to grab your activity manual pages for 11-2. I told you to have 11-2, 1, 2, and 3. I think we're just going to do 1 and 2. We're going to try to get through both of those today. 3 was just kind of a bonus one anyway. It would be good to do on your own, but it's not necessary. We're going to be doing tree diagrams and organized lists. Anytime you want to talk about the outcomes for an experiment, it's good to organize your sample space. There are different ways to do that, primarily tree diagrams and organized lists. The more organized you are, the easier it is to use your data later. Now, for many experiments, if you're doing multiple stages, like I just said, it's important to list all the outcomes in the sample space. It's easier if you're able to do that with some type of organization. A tree diagram is a really good way to organize that. That's going to resolve in just a second, guys. Okay, there we go. So think about flipping a coin 2 times, or 2 coins once. But either way, we're talking about 2 coin flips. Now, these are just standard coins, so the result of each flip is either going to be heads or tails. Well, if I have heads on the first flip and tails on the second, then that would be the outcome, heads, tails. What's another possible outcome? Heads, heads, tails, tails, or tails, heads. Anything else? No, that's really it. Either I'm going to get heads on the first one and then either tails or heads on the second, or I'm going to get tails on the first one and then either tails or heads on the second. So I've got 4 different outcomes in my sample space. Now, Saida, yes.
Isn't head, tail, and tail, head the same thing?
Okay, that's a good question. It comes out to the same number of heads and tails.
Mm-hmm.
But it was derived in a different order.
Okay,
So it's not the same outcome.
So
yeah.
we are taking each coin separately.
Yes.
Like a red coin and a green coin.
Right, there you go. Just like we did our red and green die. We count 4, 6, and 6, 4. We record it differently.
Mm-hmm.
Even though they both give us a sum of 10. And if you think about that, when you think about doing like a multiplication chart or an addition chart, you see the same thing happening. If I'm going to do 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 1 plus 2 is 3, 2 plus 1 is also 3. I'm getting the same sum, but I'm starting with the digit in a different row.
Got it. Okay, thank you.
So I'm going to have, okay. All right, so if you're talking about the number of outcomes in the sample space, you want to make a difference between those 2 outcomes so that you list them both. Now, if my question is, how many ways can I get exactly 1 heads? Well, there are 2 ways for that to happen, because in my question, it doesn't matter whether heads showed up first or second. All right, another way to organize outcomes is with this tree diagram. Hopefully you can see why it's called a tree diagram, because it looks like branches, right? Looks like branches on a tree. So explaining how the tree diagram was made, well, it shows the outcome from the first coin flip and then the possible outcome on the second coin flip, tying it into what happened the first time, so that I have 4 distinct branches. I have one possible outcome would be heads, heads. Another possible outcome would be heads, tails. A third possible outcome would be tails, heads. And then that 4th and final possible branch would be tails, tails. So I have all 4 outcomes shown, but I just kind of follow my branches to get there. Now, because it shows all possible outcomes, this diagram shows us our sample space. Any questions on that? Now, next we're told to compute the probabilities and talk about how we got each answer. So I want you to give me the probability of getting heads on both coins. Let's do that first. What is the probability of getting heads on both coins? One out of 4. How did you get that, Saida?
Because there are only 4 outcomes and it's one of them.
There you go. Theoretical probability, we compare the favorable outcomes that match our event to the total number in the sample space. Excellent. All right, so somebody else help me out. How about the second one, the probability of getting tails on at least 1 coin? Now that at least 1 is important. If I'm interested in the probability of getting tails on at least 1 coin and I'm doing 2 coins, then I'm interested in all of the events in the sample space that have either 1 or 2 tails, because that gives me at least 1. Shanique, perfect. 3 out of 4. 3 out of 4. And I already kind of did the explanation there. At least 1 means that I have at least 1 or 2 tails. So the only one that doesn't fit that was when I have heads on both coins. So these are complementary events. If I add the 2 probabilities together, I have the entire sample space. Getting heads on both coins, that was the first event. Getting at least one tails is the complement of that event because that consumes the entire sample space. Now the next question challenges us to draw a tree diagram for 3 coins, so that we are going to do 3 different coin flips, and then we're going to figure some probabilities from that. So when you do your tree diagram, make sure you give yourself plenty of space to draw all the branches. So my first outcome, heads or tails, and then no matter what I get on that first toss, I can get either heads or tails on the second toss or on the second coin. And then for the third toss or the third coin, I have the option of getting heads or tails again, because one toss, the outcome does not affect the next. Each time I have equal chance of getting heads or tails. So how many different outcomes are in my sample space if I'm going to flip 3 coins? Shanique and Saida, that's right. We have 8 possible outcomes. Now let's think about this for a second. When I was doing 2 coin flips, for the first flip, it could happen 2 ways, either heads or tails. For the second flip, it could happen 2 ways, either heads or tails. So I had 4 possible outcomes in the sample space. When I'm doing 3 coin flips, then I have 3 blanks to fill in, and each time I flip the coin, it could be heads or tails. So I've got 2 possible outcomes each time for a total of 8. So basically, when I'm flipping coins, I can calculate 2 to the n power, where n is how many times I'm going to do that coin flip, to see how many outcomes there would be in my sample space. If I wanted to list, so this is my tree diagram. If I wanted to make an organized list of my sample space, I would just read across each branch. Some of us like to work from an organized list better than we like to work from the tree diagram. Some of us, it's not going to matter. Just know that you have options. So we have our tree diagram right next to our organized list. Both of them give us our sample space with 8 total outcomes. So somebody help me out. Let's number these. You know what? Let's do ABC. Pick one of these to work on and give me a guess. In chat, answer either A is or B is or C is, and give me a probability that's you think that works for what it's asking. Make sure you read carefully. Exactly is not the same as at least. All right, so Shanique says that A is 1/4. Since we have 8 total outcomes, that means you came up with 2 outcomes, right? So you would have started with 2 8s on A, exactly 2 coins. So if we had exactly 2 coins, I see 2 heads on exactly 2 coins. Sorry, so exactly 2 heads. I've got exactly 2 heads, exactly 2 heads. There is another exactly 2 heads. Shanique, which one of those did you not see?
The middle one, the heads, tail, heads. So that would be
split.
Yes.
Yeah. But you were counting right. You just missed one.
Yep.
That's important. So you understood what we were doing. We just sometimes are fallible people, right?
Right.
And then Saida said 4 out of 8 for at least 2 coins. Saida, how did you get a total of 4? There's my 3 that have 2 heads. Where's the 4th one?
The top one, because it says at least, it doesn't say exact.
There we go. At least means 2 or more. So in this case, that means 2 or 3 heads. So there are 4 possible outcomes that fit that probability. And then Phyllis said exactly 2 heads in a row would be 2 eighths. And Phyllis, those are the 2 that Shanique had found for the exactly 2 coins, right? Those are the 2 that it's easy to spot right there. We've got 2 heads in a row here and 2 heads in a row there. Exactly 2 heads in a row. We don't count this one because that has 3 heads in a row. Now, I like that Shanique had simplified for us and given us a reduced fraction. 2 eighths is going to simplify to 1/4. 4 eighths is going to simplify to 1/2. In Wiley Plus, I think they do ask you to simplify those final answers, so that's good to keep track of. When we are making sure we've got the count right, sometimes it's easier to talk about it before we simplify. Phyllis, yes?
Okay, so on A, when they say heads on exactly 2 coins, why don't we count the one that got 3?
Because exactly 2, this is not exactly 2, this is 3.
Okay, so if it say at least 2, then we can count one that got more than 2. But
Yes.
Okay, I understand now.
Yeah, and that's why we do these practice pages, so that we start noticing that those little words that we sometimes slide right past absolutely matter. All right, next page, we're going to talk about colored blocks. Now, you could make colored block. I mean, you could like do colored pieces of paper. You could do there's material cards. You could cut them out and color them. But I have complete confidence in you that you can probably do this one because we're just setting up the possibilities. We're looking at the sample space. We're not doing the experiment. How many total blocks do I have? So if I've got them in a jar or in a bag, how many blocks are there?
4.
4 blocks. Yep, 4 blocks. How many times am I going to draw? Two draws. Thank you, Shanique. I'm drawing 2 blocks from the set of 4. Now, I make my first draw. I pick out my block. Where does it go? Does it go back in the jar or does it go off to the side?
Return it to the pile.
Return it to the pile. Now that's important because that means we are working with replacement. So for each draw, we have 4 blocks to choose from. So if I look at my first draw, these are the 4 blocks I have to choose from. To complete this by representing the second draw, I need to draw 4 more branches from each of these because I still have blue, blue, red, yellow to pick. How many total outcomes are going to be in my sample space?
Too many.
Bunches, right? So let's think about that. I'm drawing 2 times. In the first draw, I have 4 blocks to choose from. There you go, Phyllis. The second draw, I have 4 blocks to choose from. So the number in my sample space is 16 total outcomes. All right. I'm depending on you guys to ask questions if you come across something that we're talking about that you are not catching. So there are 16 outcomes in my sample space. If I wanted to list them as an organized list, I would say that first one would be blue, 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 red, blue, yellow. Then the second one, again, the same thing, right? Because we had 2 blues to start with. Red, blue, red, 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 yellow, yellow, blue, yellow, blue, yellow, red, yellow, yellow. So there's in my organized list of the 16 different outcomes. I took it straight from my tree diagram. So that's B. That is listing the outcomes in the sample space right there. Now we're going to use the tree diagram to compute some probabilities. Let's do it again. I liked that. Let's do A, B, C for our probabilities. We know we're doing theoretical probabilities. We're not actually doing the experiment. So our denominator is going to be the number in the sample space. Pick one to work on, A, B, or C. See what you get. Don't reduce to start with so that we can all compare the count. A is 12 out of 16. Good job. There, 12 of our 16 outcomes have us drawing at least one blue block, which means either one or two blue blocks. In fact, it might be easier to say, okay, which ones don't have a blue block? And so that you come up with just these 4 that don't have a blue block, which means the other 12 all do. Good job, Phyllis. Let's see. 6/16 is B. 6/16 is B. Make sure that you find all of those. Now, notice that it's 2 blocks of the same color. So either both blue, both red, or both yellow on B. So both blue, right here, these 4, both red, both yellow, 5, 6 outcomes for B. C is the set of outcomes where we have exactly one blue and exactly one yellow, and Shanique, that's correct, 4 out of 16. Exactly one blue and exactly one yellow, blue, yellow, blue, yellow, blue, yellow, blue, yellow. Order didn't matter. Exactly one of each. And now that we have confirmed that we've got the counts right, we can go ahead and reduce. If I reduce by 2, I have 6/8. I can go again. Slowest terms here would be 3/4 for the probability of drawing at least one blue block. 3/8 for drawing exactly 2 blocks of the same color. And then for C, it would be 1/4. And see, when I start comparing probabilities, when I'm trying to compare, well, I can compare these two really quickly and easily because they have the same denominator. But when I have a different denominator, it's just more of a struggle to see how it compares to the other probabilities and than it is looking at them all with the same denominator. Any questions about number 2? That was with replacement. We're drawing with replacement. Number 3, we're going to use the same starting place, but instead of drawing with replacement, now we're drawing without replacement. So my sample space has changed. My first draw, I have 4 blocks to choose from. How many are available for my second draw? That's right, just 3. So my sample space just has 12 outcomes. There are only 12 outcomes in the sample space because I'm not using replacement. When I draw a block out, it stays out. It doesn't go back in for the second draw. Now that is going to change what this second draw looks like. For example, it gave us, if you've already drawn that one yellow block, it's not there to choose again. You only have blue, blue, red to pick. So I'm going to go through and I'm going to make that second draw adjusted for whatever color was picked first and not put back in. It does not ask us to make an organized list, and my document froze again. All right, guys, mine on my screen has frozen. I want y'all to go ahead and if you want to make the organized list, you can, but you don't have to. I want you to go ahead and we'll call these A, B, C. Let me see if I can make mine unfreeze. I'm about to decide it is my Google. It's a Google issue. Okay, I am back. Let me share it again. All right, super. Anyone have answers for me? Phyllis, you said A is 10/12, so that's perfect, yes. A is 10 out of 12. 10 out of 12 of our outcomes involve drawing at least one blue block. What about B or C? B comes out to be 2/12, yep. Only 2 out of the 12 outcomes have exactly 2 blocks of the same color. And then C is 4 out of 12. Exactly 1 blue and 1 yellow. And then if I choose to simplify, if I'm asked to put these in lowest terms, that's what they would be in lowest terms. But lowest terms is not necessary for our discussion. Just pay attention to what Wiley wants from you. All right, any questions before we move on to the next page? All right. Number 4. When you're computing the probability of an event, you need to know the number of outcomes in the event. So the number of outcomes in the sample space. So we need to know what our experiment, if we were to perform the experiment, what it would look like, what that event is made up of. And we need to know what the outcomes in the sample space will be, how many there will be. We've already talked about this. We said that if we are flipping a coin, there are 2 possible outcomes for each flip. So if you flip it twice, there's a total of 4 possible outcomes. If we were going to flip a coin 4 times, 1, 2, 3, 4 flips, well, there's 2 possible outcomes for each coin flip. So that leaves us with 16 outcomes in our sample space. And I told you, since it's coin flips and each one is 2, we could think of that as 2 to the 4th power is 16. Now, only with coin flips, off the top of my head, are we guaranteed 2 outcomes each time. Maybe a true-false question, they have 2 outcomes for each question. But other times, there's going to be different number of possibilities. When I was drawing the 2 blocks without replacement in that last problem we looked at, there were 4 possibilities for the first draw, but since we didn't replace, there were only 3 possibilities for the second draw, which means there were 12 total outcomes in the sample space. Phyllis.
Okay, so you know how when we did the first example and they were complementary of each other, is there any language or terminology that we can look for to let us know if it's going to be complementary or not?
No, there's really not, because it depends on each experiment, on each situation. If we're drawing blocks, if we're picking stocks out of a drawer, if we're choosing meal combinations, it totally depends on the situation and what the probabilities are that are being asked. You know that you have complementary events when there's no intersection, so that the 2 events don't have any answers in common. And when I look at them, they include the entire sample space. So part of the sample space is in one event and the rest of the sample space is in the other. That means the 2 are complementary. But no, there's no keywords. Sorry.
Oh, okay. Thank you.
That would be nice. There's just too many possible ways to have situations set up for that, though. Okay, so what we're looking at are examples of the fundamental counting property. And there is an activity that I gave you guys to work on your own, and then I gave you a video over talking about counting choices that deals with the fundamental counting property or the fundamental counting principle. And here that is defined. That's something to make sure that you know how to calculate. If you have an event that can occur in R possible ways, and for each way, the second event can occur in S possible ways, Then in succession, you're going to multiply R times S. What we were doing here to calculate sample size, sample space, the number of outcomes, is doing our fundamental counting property. So let's look at some examples of this. If I were going to roll 2 dice, well, I'm rolling 2 dice, so I have 2 blanks to fill. And if they're regular dice, there's 6 different outcomes on each one. So the sample space is going to have 36 total outcomes. What is this one going to look like if I roll a die and then flip a coin?
So the dice is 6 and the coin is 2. So 6 times 2?
Yes. So there would be 12 outcomes in my sample space. What about this one? We're going to spin this spinner and then roll a die.
The spinner has 4 and the die has 6.
Yep. So you are looking at 24 possible outcomes in your sample space. So an outcome would be red 1, red 2, red 3, red 4, etc. And then yellow 1, yellow 2, yellow 3, etc. Okay, what about this one? We are going to draw a block from the set and then spin this spinner. Someone else help me out. What are we going to do? How many outcomes? We draw a block and then spin the spinner. That means we're doing 2 different events. How many outcomes are there from drawing the block? 5, and we already said our spinner has 4 outcomes. So in that case, we would have 20 different possibilities, 20 different outcomes in our sample space. Some of the problems that you're going to see on the activity that I have for you in Blackboard to work on, something like choosing an outfit. If when I pack my suitcase, I consider an outfit to be shirt, pair of pants, and shoes. I'm going to pack 5 shirts, 3 pairs of pants, and 2 pairs of shoes. And it's a different outfit in my mind. If I do one thing differently, how many different outfits can I create? Shanique, that's right. 30 different outfits. 5 times 3 times 2. I've got 3 different choices to make. I have to pick a shirt, a pair of pants, and shoes. And I multiply together the different ways I can pick each different piece of my outfit. What if I'm going to pick a password, and the password needs to be made up of, in order, 2 letters, then 3 numbers, and I'm not going to allow repetitions. It's not really a well, yeah, a login password. 2 letters first, then 3 numbers, no repetitions allowed. Well, how many blanks am I going to have to fill? How many choices will I be making?
5.
5, yeah, 5 different blanks to fill. The first 2 are going to be letters, and then the last 3 are going to be numbers, and I can't repeat. So how many letters are there to pick from to start? Assuming we're using our alphabet, our English alphabet.
Now I'm singing ABC in my head and counting it.
Yeah, yeah, exactly. How many letters are Phyllis? Yes, 26 letters in the alphabet. Let's see, I picked P first for Phyllis because she gave us the answer. How many letters can I pick the second one from? 25. There we go. Now I have to switch to numbers. Pick up your phone or your calculator and look, how many numerals are there? How many digits are there available?
10.
10, because you got 0 through 9, right? And it's not replaceable, no repetitions. So there we go, Judy, good job. 10, 9, and then 8. Put that into your calculator. How many different passwords can I come up with if these are the restrictions? How many passwords are possible if those are the restrictions? Oh no, way more than that. You're multiplying all of those. What do you guys get when you multiply that out? There you go, Shanique. Yeah. Phyllis, I think it's 468,000. 468,000 different combinations, different passwords, if those are my requirements. Okay. All right. Oh no. That's not helpful. Technology has not been my friend this week. I'm just going to throw that right out there. Okay, so we're going to keep talking about tree diagrams, but we're going to spend the rest of the time we have for today talking about probability tree diagrams. Now, I went through the homework for this section 11.2, and I think that by the time we work with the probability tree diagrams, that should cover most of the questions that you should have about the homework. If I'm wrong, if there's something that I didn't cover, I will try to stop. We may not get all the way quite to the end of this activity manual and give a little bit of time for questions at the end in case there's something that I don't get to. But we introduced the class today talking about probability tree diagrams. So we're kind of off to a good start. We looked at what a probability tree diagram would look like and compare these two. These represent the same information. This is not probability. We've got 4 different possible blocks to choose: blue, blue, red, yellow. This is a probability tree diagram. Notice that I combined the blue blocks into one branch. Now I want to take issue with that, and instead of writing 1/2, put it as 2/4, so that you know you got 2, 3, 4 blocks. 2 of them are blue. Eventually we will get to lowest terms, but we are not going to start by putting things in lowest terms because that just makes things more difficult for us. So I'm going to change that 1/2 to 2/4. This is the first experiment, or the first experiment that we worked with on the other page, where we were doing the 2 draws with replacement. So the first draw had 4 blocks and the second draw had 4 blocks. So the first draw has 4 blocks. We're going to illustrate the second draw using a probability tree diagram, also with 4 blocks, because we're allowing replacement. So we're still going to have blue, blue, red, yellow. But we're consolidating those 2 blues into one branch. It makes it a little easier. You don't have as many different possibilities to count. Since it's with replacement, our fractions aren't going to change. We're still going to have 2/4, 1/4, 1/4 all the way across. Because we replaced the one, whichever one we picked, we put it back in the draw for that second time through. Now I can calculate a probability for each branch by multiplying the 2 probabilities together. All right? 2/4 times 2/4 is 4/16. 2/4 times 1/4 is 2/16. When you multiply fractions together, you multiply numerator and denominator. Now I want to double check and make sure that I've done it correctly and I've got my entire sample space represented. So I want to think about adding all of these probabilities together, and what I should get would be 16 out of 16, or 1 whole thing. I've got all possible outcomes. So 4, 6, 8, 10, 11, 12, 14, 15, 16. So we know we've done the multiplication correctly. Does anyone have questions about what I did to get these probabilities for each branch?
No, but I'm gonna take you back a little bit. The 2/4, we put 2/4 because we have two blues. So instead of doing two branches, we did one, but wrote 2/4 on it, right?
Correct. Yeah. So we simplified our tree diagram. So we only have 3 branches instead of 4.
Okay.
And we've already started counting probability.
Got it.
Yeah. So instead of having to do that big organized list and count every individual outcome, I can multiply the probabilities, and it's going to make life a little easier.
Okay. Thank you.
No problem. Okay, so we got the probability for each of my outcomes, each of my branches, and I double checked myself, and yes, it added up to 1, 16/16. So using my outcome, my probability outcome tree diagram, I can see that RR, red and then red again, is one branch. I don't have to look for multiple branches. It's just one possible outcome. And the probability of that one branch, that one possible outcome, red, red, is 1/16. Any questions about this introduction? The top of the next page describes this process of how we find the probability of each branch. It gives us the term for it, multiplicative property of probability. You can find the probability of an outcome by multiplying the probabilities on the branches for that outcome. And we already did E. We added the rows, the bottom row, we found the sum of all the probabilities. And we noticed that the sum is equal to 1 because we've included all possible outcomes. We have our entire sample space represented. All right, number 2, this next section wants to emphasize to us that we have simplified our probability. We've simplified our tree diagram when we condense it by using probabilities. If you want to compute the probability of drawing a blue and a red in any order, I would have to consider these 4 different paths. There's a blue-red, there is a blue-red, there is red-blue, there is red-blue. So there are 4 different paths to consider. But if I use the probability tree diagram, I've only got 2 paths to consider because I have condensed and put those 2 blue outcomes together instead of having 2 separate branches. Now they have simplified to 1/2 and 1/4, and that's okay. But again, it can make it easier to not simplify until the end. I want to encourage you not to worry about simplifying until the end. If I look at this, I've got 1, 2, 3, 4 different paths out of 16, so that would be 4/16, or 1/4 would be the probability of drawing a blue block and a red block in any order. If I look at my second option where I've got my probability tree diagram, well, I've only got 2 branches to consider instead of 4. I've got 1/2 times a 4th. 1/2 times a 4th is an 1/8. And then I've got another one over here. 1/4 times 1/2 is also an 1/8. And I'm going to add those together, which gives me the same result. Now notice that I did 2 different steps here. I found the probability of a branch by multiplying, And then I added together the two different probabilities. So the probability of this first branch is 1/8. The probability of the second branch is 1/8. And I found the sum of those two, the total, to get the probability of this particular type of outcome. That is what we're going to call the additive rule, or the additive property of probability. If you look at the top of the next page, the probability of an event by adding all the probabilities of the outcomes is the additive property of probability. So we're going to use that multiplicative and additive property. We're going to use them both together to help us find the probabilities of different outcomes. All right, we're going to have to look back at the tree diagram, the probability tree diagram that we already have. We want to find the probability of drawing at least one blue block and 2 blocks of the same color. So what you might want to do to start would be to find the probability of each branch. Now we've already gotten a start because we said, okay, this one is 1/8 and this one is 1/8. 1/2 and 1/2 is 1/4. 1/2 and 1/8. 1/2 and 1/4 is 1/8. That one would be 1/16. And you see I've got different denominators since they simplified, and it's going to make life just a little bit harder for me. So there are the 1, 2, 3, 4, 5, 6, 7, 8, 9 different branches that represent all of those combined probabilities. So what do you think? I'm trying to get everything on the screen. What is the probability of drawing at least one blue block? Now we've talked about that keyword at least. That means out of my 2 draws, I need at least one. So either one block to be blue or both blocks to be blue. Well, that's going to include all 3 of these pathways. So I'm going to use all 3 of these probabilities. 1/4, 1/8, and 1/8. Because that's at least one blue block, all 3 of those. And here's another pathway with a blue block. And then here's another pathway with a blue block. So all 5 of those pathways, 1, 2, 3, 4, 5, include at least one blue block. When I add those up, what do I get? Well, I have to have a common denominator, don't I? So instead of thinking about this as 1/4, I'm going to think about it as 2/8, because that's the same thing. There you go, 6/8. 6/8. And if they're wanting it in lowest terms, then I would reduce to 3/4. What about the next one? Drawing 2 blocks of the same color. Well, if there are 2 blocks of the same color, then I'm looking for the pathway that are both blue, both red, both yellow. So I'm going to have 3 different pathways that I want to add together. Well, both blue would be right here, both red would be right here, and both yellow would be right there. And again, I need to have common denominators to do my addition. Right, Phyllis, that's right. It's going to be 6 out of 16. I would need to think of this as 4/16, 4, 5, 6 16ths, which if I simplified would be 3/8. Okay, this went quicker than I thought. So we've got about 12 minutes left before I have to jump off so that I can prepare for my next class. I'm going to offer you attendance. Faith, you saved me. Thank you so much. So here we go. Let's try this. And here's the attendance file. The question I want you to answer, are you ready for this? The question I want you to answer for me in the attendance is, why don't we reduce fractions when we're doing those probability tree diagrams? Why would I want to not reduce while I'm doing the diagram and wait and reduce at the end? That's the question that I want you to answer for attendance. Okay. We talked about that at the beginning, and we've just been talking about that. So somebody check that file and reaffirm for me that the link worked. And in the 10 minutes we have left, do you guys, thank you, Shanique, do you guys have homework questions that you want to cover? Or do we want to do this last one, the number 3? If we don't do number 3 today, we'll start class with it on Tuesday. So it's going to get done no matter what. Does anyone have a specific homework question they want to ask?
Yes, I had a question. Hold on, let me see if I can go find it. I thought I had it open. It was actually the very first one. It was the test question 4, and I don't know why I'm having a hard time with it, but I am.
So I don't have the homework list.
Okay.
I will need you in the future try to find them in the book so that you can give me like a page number or a question number.
Okay.
But you can guess what the question was, and I can try to find one like it.
Okay, it's chapter test question number 4, and the question is, how many outcomes are in the event toss 2 dice and 3 coins?
Oh, okay. We can talk about that.
Yes.
2 dice, 3 coins. Okay. So if we're going to do this, we're doing 5 different things. 2 dice, 1, 2, 3 coins. How many outcomes are possible for each of the die?
6.
How about a coin?
2 for each.
Yeah. So that fundamental counting principle, you're going to multiply them together.
Oh, I don't know what in the world I was doing. Okay, got it. Thank you.
Okay, no problem. Anything else? Anyone else? So I know most of you don't have a physical textbook, a paper textbook, but you remember you have the ebook. So as you go through the homework in Wiley, if you get stuck, come to the end of the chapter and find there's going to be a problem set A and a problem set B. If you will find a similar question in the textbook, then you can reference me to that question, that page number or the question number, and I can put it on display and we can talk about a similar problem to the Wiley problem. Any more homework questions? Okay, so we're going to spend our last few minutes working this out then. We're going to draw a probability tree diagram for an experiment and then talk about how we're going to compute probabilities from it. I hit my autofocus button, so it'll be back with us in just a second. Okay, so we're going to randomly draw 2 blocks without replacement, so our numbers are going to change, from a set containing 3 green, 1 white, 2 orange blocks. So 3, 4, 5, 6 blocks. There will be 6 blocks available for the first draw, 5 blocks available for the second draw because it's without replacement, which means there would be a total of 30 different outcomes in our sample space. But because we're going to do a probability tree diagram, we won't have 30 different branches to have to consider. We'll consolidate all the greens on one branch and all the oranges on one branch. So for our first draw, we've got 3 colors. We've got green, white, and orange. 3 of the blocks are green, 1 is white, and 2 are orange. And again, I'm not simplifying to keep things easier for myself. Now when I draw make the second draw, even if I drew a green block, there's still going to be 2 left. So I still have green, white, and orange. If I drew a green on the first draw, there would be 2 out of 5 blocks left that are green for the second. I've still got my one white block and my 2 orange blocks. And I can see that I've got 2, 3, 4, 5 blocks represented. Now, if I draw a white block on the first draw, I don't have any white blocks left. So the only color blocks I could draw on the second draw here would be green or orange. You guys do orange outcomes. I'm going to give you a second before I put mine up. Ask me questions if you don't understand what I did. And notice that I'm spot checking as I go. I've got 6 blocks represented here. I've got 5 here. I've got 5 here. So I'm going to make sure I have 5 blocks represented here. I didn't simplify anything because it's going to make this next part easier for me. And before I do anything else, before I even start looking at the questions I need answered, I'm going to calculate the probability for each branch using the multiplicative rule. So when I do that, let me ask you this. What's the probability for this first branch, green, green? Yes, Phyllis, that's it. 6 out of 30. That's my probability for the first branch. And my denominator, because I haven't simplified anything yet, my denominator is going to stay 30 for everything. It's going to make life easier. And I know that the sum of this should equal the entire sample space, all 30 outcomes, so I can spot check again and make sure that my numerators are all going to add to 30 so that I have the entire sample space represented in my probabilities. Okay, I'm open to questions whenever you have them. Now here's what I'm going to do next. I'm going to give you the answers in simplified form. And I want you to work them out and see if yours match mine. And if they don't, ask me and we will figure it out together. So we'll go ahead and we will talk about these as A, B, and C again in case you need to reference one. So I've given you the simplified answer. And you need to see if you get what I got. And if you get what I got, we're awesome. That's great. And if you don't, we need to talk about it. You just have to say, how did you do B? Or how did you do C? Okay, so Shanique wants to look at B. No green blocks. So if I have no green blocks, I'm going to choose green color. Oddly enough, well, no, I'm not going to use green. Let's use purple. Okay, no green blocks. Well, green. I'm not going to use that. In fact, I'm not going to use any of these because that means I'm picking a green first. So no green blocks is going to eliminate these first 3 branches. I'm interested in this branch because that is white and orange. And I'm interested in orange green, and I'm interested in orange orange. Those are the 3 branches that have no green blocks picked. So I would do 2/30, 6/30, and 2/30, which is 10/30. Oh, look at that. That should be, did you get 1/3? 6, 7, 8, 9, 10?
No, I was just gonna say, so the one where you circled 6/30ths, wouldn't that, because orange green, isn't that a green block? Wouldn't you draw?
That's a green. Thank you.
Right? Okay, yeah.
That should be a 2/30th.
Got it.
I don't know. Like, I would love to say, oh, I did this thing. Or if I was really smooth, I would say, oh, I'm so glad you caught that. I was waiting to see if you would. I don't lie though. That was just an honest mistake. 2, 4, 6. There we go. So I've got 6/30ths, which does reduce to 1/5. Thank you. You just thought I was going to help you. You were going to help me. So our 3 outcomes that don't include a green block are those 3 that I have circled, not the one that is hidden under my finger because I messed up. Does anyone need to see A or C while we still have a minute or 2 left? Phyllis, yes, it was 6 out of 30, which then simplifies to be that 1/5. Oh, A is also 6 out of 30, which simplifies to 1/5. Yes. And then B would have been 22/30ths, which simplifies to 11/15. Okay. I am unfortunately pretty much out of time. If I were doing this over again, I wouldn't schedule back-to-back classes. But I am supposed to meet at 2 with my college algebra students. So does anyone have a final question that they want to ask before we get out of here today? There is the Google form just to get it out in chat one more time. All right.
Can you please repeat the question, Ms. Kimball?
Sure. The question for the attendance is, tell me why we don't reduce on these probability tree diagrams. Why don't we reduce our fractions when we're setting it up?
Okay. Thank you. You have a good day.
You too. All right, guys. I'm going to stop our recording and we will move